research arching our way of life. They heal the sick, make our labors more efficient, improve the quality, and perform untold chores in agricultural, medical, and industrial research. What are radioisotopes? They are merely unstable forms of elements giving off unseen particles or rays from the nuclei during the process of changing to stable form. Alpha particles, which are not very penetrating, can be stopped by a sheet of paper. Beta particles move a few feet in the air and can be halted by a relatively thin piece of wood. Gamma rays, the most penetrating of the three, travel long distances in air and can be stopped only by a large amount of heavy material shielding, such as lead or thick concrete walls. Radioisotopes emit one or more of these types of rays. The rate of emission, related to a characteristic of radioisotopes, the half-life, varies widely. The half-life of normally available radioisotopes ranges from hours to thousands of years. Potassium-42, for instance, has a half-life of 12 hours. While carbon-14 has a half-life of more than 5,000 years. This means that one-half the potassium-42 has decayed after 12 hours. But it would take 5,000 years for one-half of a carbon-14 sample to decay. Three methods of producing radioisotopes are by simple neutron capture with gamma-ray emission, by fissioning of uranium atoms, and by transmutation, which means the capture of a neutron and the ejection of a proton. In simple neutron capture, a stable isotope, such as cobalt-59, is bombarded by a neutron. In absorbing the neutron, the isotope becomes radioactive cobalt-60 and gives off a gamma ray. During fission of U-235, for instance, heavy uranium atoms split into both stable and radioactive isotopes. They may break down in a variety of ways to give, eventually, radioisotopes with long enough half-lives so that they can be separated. Strontium-90 and cerium-144 are two examples. Finally, in transmutation, fast neutrons enter the nuclei of atoms and cause the ejection of protons. This changes the identity of the element. For example, sulfur-32 becomes phosphorus-32. Oak Ridge National Laboratory pioneered the production of radioisotopes in 1946 with the processing of iodine-131 and carbon-14. The laboratory, the largest producer of radioisotopes in the world, now offers more than 300 radioactive and stable isotope products. At Oak Ridge, radioisotopes are produced by irradiating elements in reactors and by the extraction of fission products from highly radioactive wastes obtained during the processing of spent reactor fuels. The most widely used method is through irradiation in reactors. Elements are prepared as target materials in small containers of various sizes. The container, after being cleaned, is loaded with the element to be irradiated. The cap is crimped and the container placed in a graphite stringer, such as this model, for insertion into the reactor. If the material is to be inserted into a water-cooled reactor, the elements are first sealed in a quartz ampule and the container welded. Such target materials become radioactive by neutron capture. They may also become radioactive by transmutation, as in the case of phosphorus-32 production. In producing phosphorus-32, an aluminum container lined with platinum to prevent corrosion of the metal and contamination of the target material is filled with sulfur-32. The unit is then loaded into a fuel element, similar to this, for irradiation in the low-intensity test reactor. After 3 weeks of neutron bombardment, the target material is ready for separation of phosphorus-32. The mixture of phosphorus-32 and sulfur is then moved to a hot cell for processing by distillation of the sulfur. Thick concrete walls and a leaded window protect the operator from radiation during these operations. Iodine-131, like several other short-life isotopes, is produced in the fissioning of uranium. Fuel slugs are loaded into the graphite reactor and bombarded by neutrons to create a chain reaction. About 3 months later, the fuel slugs are removed and hauled in a protective carrier to the iodine processing area. Behind heavily shielded walls, the slugs are dissolved in acid and the iodine distilled from the uranium solution in a series of operations. After radioisotopes are processed, they are transferred to the packaging area for analysis and storage or shipping. Radioisotopes in liquid form are stored behind a 20-inch concrete barricade. In preparing a shipment, the operator maneuvers the highly radioactive material while viewing the operation through mirrors, another safeguard against radiation. The storage bottle is moved to the transfer area, where a pipette withdraws the correct amount of isotope and transfers it to a shipping bottle. Tightly capped, the bottle is then placed in a protective container. The shipping package is checked for possible radiation and contamination, and the package is prepared for delivery. A variety of containers is used since the activity of source determines the size of the protective carrier. Since short-life radioisotopes often must be sent considerable distances, a close check on transportation schedules is maintained to ensure prompt delivery. Important non-radioactive products offered by the laboratory are stable isotopes. Stable isotopes are enriched by accelerating electrically charged ions in a calutron. When the ion source is placed between the poles of an electromagnet, the fast-moving ions are deflected to a greater or lesser degree depending on their masses, and then collected in receiving pockets. This method provides usable quantities of the less abundant isotopes and higher purities of all isotopes. One of the major uses for stable isotopes is the production of high specific activity radioisotopes. The most recent significant development in the isotope field is the large-scale separation of long-life fission products. Such products are produced in kilocurie quantities in Oak Ridge National Laboratory's Fission Products Pilot Plant. The feed material is nuclear waste obtained during the processing of spent reactor fuels. This unique pilot plant, known as F3P, is designed to process nuclear waste solutions by separating, purifying, and packaging the fission products individually. The plant was built to satisfy a growing demand for long-life radioisotopes and to develop large-scale fission product separation processes. The facility is equipped to handle, with minor changes, most types of wastes. The plant's 9 cells in the North Bank contain equipment for chemical processing. 6 South Bank cells hold equipment for final purification and fabrication of radioactive sources. The chemical processing cycle begins with the feeding of waste material into the evaporator, where the volume is reduced considerably. From here, the concentrated feed flows to the first of 4 identical cells, each containing a precipitator, centrifuge, centrifugate collection tank, and a fraction tank. After the concentrated feed has entered the precipitator, gaseous ammonia is added while the solution is being thoroughly agitated. The precipitated slurry then flows to the centrifuge, where the liquid phase is separated from the solids which adhere to the wall. The effluent from the centrifuge flows to a collection tank. Nitric acid is then added to dissolve the cake material. This solution, containing ruthenium-106, is stored in the cell's fraction tank for later processing. This precipitation and centrifugation process is alternately repeated in 3 similar cells. The effluent from the initial collection tank then flows to the next cell, where cerium-144 and promethium-147 are removed. When the procedure is repeated once more, strontium-90 is obtained in the fraction. Technetium-99 is separated during the 4th precipitation and centrifugation process. Effluent from the centrifuge in this processing step is sent to batch crystallizers for separation of cesium-137. Here, ammonium alum is added to the solution. The solution is heated to 90 degrees centigrade, then cooled and agitated, causing the formation of crystals containing cesium-137. After the crystals have settled, the remaining solution is filtered and transferred to a second crystallizer, where the procedure is repeated. This removes most of the cesium remaining after the first crystallization step. The initial crystal bed is dissolved in hot water, and the solution directed to a similar unit, where cesium alum is separated from ammonium alum. Following this separation, the cesium alum is transferred to a solids processing cell for final purification. Here, through a precipitation process, cesium alum is converted to cesium chloride. The cesium chloride is then dried and the powder pressed into pellets. Cesium pellets are packaged in double stainless steel capsules for safety purposes, and the containers welded. With the packaging completed, the cesium source is inserted into a shielded carrier for shipment to the user. For the separation of cerium-144, the cerium-promethium fraction is transferred to batch mixer settlers. Here, an organic reagent is added, and the cerium is extracted into the organic phase. The aqueous phase, containing the promethium, is separated from the organic by draining to the receiver tank. This promethium solution is further purified by a second batch extraction. After returning to the receiver tank, the promethium passes to a precipitator, where it is precipitated as promethium oxalate. This slurry flows to a filter tank. After being filtered, the oxalate is dissolved by adding nitric acid. The solution is then transferred to resin columns, located at another building, for separation of promethium from other rare earth elements formed during fission. The resin beds adsorb the rare earths from the solution. The addition of citric acid to the resin column separates the rare earths into bands, which are collected separately. This separation is necessary to obtain highly purified promethium. At the F3P plant, the cerium, still in the organic phase, is removed by the addition of nitric acid. As the phases separate, the cerium is drawn into the receiver tank and then transferred to another cell for final source fabrication. The other fission products, ruthenium-106, strontium-90, and technetium-99, are put through similar final purification steps before their shipment to consumers. The successful demonstration of fission product separation on a relatively large scale can lead to construction of production-type facilities for separation of larger quantities. There are indications that production quantities of fission products will be required for many uses. Included are the pasteurization and possible sterilization of foods and drugs, initiators for unusual chemical reactions, and utilization as special power sources. The application of radioisotopes is well on its way to becoming the foremost peaceful use of our nuclear technology. Used as tracers and engaging, radioisotopes already have created significant effects on industrial economy. Radioisotope process control techniques, coupled with electronic data tabulation and automatic control devices, are expected to help speed the age of automation. As a source of high-level radiation, radioisotopes will increase the distribution of foods and industrial products, thereby helping to reduce want and to increase the world's standard of living. New industries will spring up to service and supply devices using radioisotopes and to promote many new applications. The United States, through educational and technical assistance offered under its Atoms for Peace program, helps materially to realize worldwide benefits from the atom.